Okay, so now we're looking at compounds. We're done with quantum for a while. Oh, sorry, my screen just went blank. Okay, we're looking at we're done looking at quantum for a while. We'll come back to quantum when we're dealing with chapter the valence bond theory. We're gonna come back to the orbital diagrams and go over that again. We're dealing with the third theory of bonding. Okay, the second and the third beyond Lewis. Okay, molecules and compounds. When we're looking at this here, we're talking about how molecules are held together, and they're held together by chemical bonds. So we're talking about atoms combined with chemical bonds to form compounds, right? So I'm going to be looking at ionic, covalent, and metallic bonds and why we see these kind of bonds, right? And these bonds are not black and white. They kind of merge into each other. When we're talking about basic chemistry, maybe elementary, non-majors chemistry, we make it sound like these kinds of bonding are so different from each other. But as we get to a higher level, we realize the bondings are actually very similar to each other. Okay, that in general, all bonds, no matter what category we're looking at, it results from the attraction of charged particles. So we will even see metallic bonds happening between two metals, metals plus metals, right, forming a bond. We will see this bond being held together by electrons attracting protons. Opposites attract. With ionic bonds, you see metals plus nonmetals. With covalent bonds, you see nonmetals plus nonmetals. But once again, regardless of the kind of bond we're looking at, fundamentally, all bonds at some level have opposite ions attracting each other. Okay? So, ionic bonds. With ionic bonds, you have metals and nonmetals forming a bond together. We're told here the bond is formed when you have a transfer of electrons from one atom to another. Okay? When this transfer of electrons happen, you have metals interacting with nonmetals, and we're told that it can transfer one or more of its electrons to the nonmetal, it referring to the metal. Okay? The metal becomes the cation, the nonmetal becomes the anion. So let's talk about size, because as we're looking at this, remember how we said in the periodic table, top right was fluorine, bottom was, let's go with cesium, because cesium is the largest. This is the largest, and this is the smallest. We said fluorine was a nonmetal, and then we said cesium was a metal. Okay? What we're seeing here is the way they bond has to do with their size. Even though we're discussing we're talking about ionic bond, it boils down to their size, because all this behavior boils down to quantum. Quantum has to do with the size and the arrangement of the electrons and everything. So cesium is a very large atom, right? So cesium is large, and cesium is a metal. Then you have fluorine that's small and a nonmetal. Okay, when they're trying to form a bond, there has to be some kind of exchange of electrons. So then as they're getting together, they're trying to negotiate. Well, who's going to give up what electrons? Now, even between the elements, energy has to be energy has to be added to remove the electron. Energy has to be lost to gain the electron. So between these two, the negotiation goes like this. Which one can easily lose the electron? Based on the size of cesium, the ionization energy is low. For that reason, cesium easily loses, in this case, based on its group number, one electron. When cesium, because its electron is so far away from the nucleus, remember it's large, electron is so far away from the nucleus, it loses easily that one electron because it's so far from the nucleus. Then it becomes cesium positive. When it becomes cesium positive, though, so we're kind of remixing what we learned in the last chapter to explain why they bond the way they do, right? When it becomes positive, we mentioned in the last chapter, when the atom loses the electron and the energy level, the remaining species becomes smaller, right? So cesium ion, yes, it gains the configuration of, let's see, where is cesium? Cesium is right here, Cs, of xenon, but it has a positive charge. So iron is smaller than it was before, but not smaller than fluorine. Whoa, not smaller than fluorine, but smaller than what it was before. Fluorine, on the other hand, started off with a positive nucleus, small in general. Fluorine couldn't be the one to lose the electron because it's small. It will cost a lot more energy to make fluorine lose the electron, but fluorine gains electrons. So fluorine gains the electron from cesium. It takes the electron in, and when it does, what happens? It gets larger. We talked about this in the previous chapter that when an element or an atom gains electron, it becomes larger because it's like it gained the new electron with a new layer, right? So in this case, fluorine, you have more electrons, more size, it's more massive. Fluorine becomes larger. So iron is larger than it was before, but not larger than the cesium ion, okay? So this is negatively charged, this is positively charged. Even though iron is larger, fluorine has the configuration of neon. What makes them attract each other is not the configuration, obviously, because they're stable now. It's the charge. Opposites attract. So here we see opposite charges attract. All of a sudden, even though they're quote unquote more stable, they have an attraction for each other. They can't fight, so they get together. So when you're simply showing this, you say cesium is positive, fluorine is negative, right? Criss cross, and then you call this cesium fluoride. Okay, so at some point we're going to be working this out to see how we get ionic compound. Remember, cesium used to be a metal, fluorine used to be, oops, it used to be a nonmetal. It had no charge. Fluorine gained electrons from Cs. Cs lost electrons to fluorine. So scientists argue that is cesium really freely giving up its electron, or is the electron being taken from by fluorine? You can look at it that way. Since fluorine is a very small atom, it has a very strong core. If you're taking organic chemistry, I'm just going to tell you this bottom line. Fluorine is very small. It has a very small core. I mean, a very strong core. Okay. Remember, the core is that attracting power. So not only does fluorine pull its own electrons, keeping them very close together and very tight, keeping the atom tight, fluorine has the habit of taking electrons from other elements. So if the elements around fluorine are not strong enough to hold on to their own electrons, fluorine will take your electrons. So in organic chemistry, where one of the things that people do is design experiments. If you want an electron taker, you bring in fluorine. So once when you really get what's going on, it's actually very interesting. It's like not really war, but it's some stuff going down. So when I got to organic chemistry, I remember they were like, "Oh, we're bringing fluorine." I'm like, "Ooh, somebody's electron is about to be taken." So when fluorine comes in, it has that habit of taking other elements' electron, right? So it's just part of the nature of fluorine. It's not personal. Yeah. Anyway, I get a little excited with this stuff. So once the oppositely charged ions attract one another, that's what's causing them to come together. You have an ionic bond. Okay. So we're told the ionic bond will then be neutral because remember, the number of ions that must combine must form a neutral compound. So I'm going to say while we're here, compounds are neutral electrically, meaning they don't have an overall charge. If they have an overall charge, they're called polyatomic ions. Okay. For the most part, once the ionic compound is formed, in this case here, we have a solid. So we're talking about the making of table salt, right? Imagine table salt is formed by chlorine gas and sodium metal, but when they combine, we get sodium chloride crystals, table salt. That's what we're eating. It just tastes good though. Now, the individual elements, nasty. Okay, what about covalent bonding? Now, think about the logic of covalent bonding, right? You got two, and this is, I mean, a lot of chemistry is my favorite chapters. I mean, a lot of them are interesting to me, but bonding is one of my favorite one because I can relate this to the people around me. I won't say names. I won't say names. I can be like, oh, this is that one friend and then the other friend. I see their relationship. It's like this. So with covalent bonding, you're dealing with two nonmetals, right? Trying to form a bond. Remember, nonmetals tend to be smaller. So imagine two fluorines. I'm drawing them a little bigger here so we can see. The nature of each fluorine individually is they're small, right? They're stingy with the electrons, and neither really wants to give up their electrons. So how do you find a compromise? Since neither wants to give up their electrons, it costs a lot of money. No, sorry, energy. Then what happens here is they share electrons as a compromise. So it's kind of like a win-win, lose-lose situation. They come very close together at this point here, and then they share electrons. So what we kind of show here is you have sharing of electrons where the atoms come very close to each other, and then the electrons are shared. This is kind of the old school way of showing it, right? The electrons are shared together, and that's how they form a bond because neither element wants to give up their electrons. They're both small. So we're told when a nonmetal bonds with another nonmetal, neither atom transfers the electrons to the other. Instead, bonding atoms share some of the electrons. And usually they share the sum they're referring to here is the valence electrons, the ones that are easily moved around for the sake of forming a bond. So we're told the covalent bond atoms compose a molecule, and so they're usually called molecular compounds. In other words, molecular compounds from non-metals. Okay, but I've seen people refer to both as molecular compounds, like both metals and then non-metals are molecules. Some people do that. Anyway, now we're looking at the chemical formula. So we're told here in general as we move on. We'll come back to metallic compounds later because metallic compounds are the ones where they're both metals, they're both given and very generous down the road. We're looking at chemical formula. Chemical compounds are usually represented as chemical formula. So here we're being told the chemical formula indicates the type and the number of each element present in the compound. Water is represented as H2O. Now, water is the common name for this chemical. Carbon dioxide is the systematic name for this chemical. And then we have sodium chloride. These are just showing you different compounds. So we'll be talking about nomenclature later on. We won't be naming common ions, but we'll be using common ions to name compounds. Okay. Then you see why we had to learn that. We're going back to how chemists communicate. When chemists are writing information and dealing with chemical formulas, there are different ways or different levels or different rationales of writing the chemical formula the way it's written. The three different ways are empirical formula, molecular formula, and structural formula. The structural formula is more significant, and we see this more in larger molecules. And therefore, we see this more in organic chemistry. Okay, we'll see it a little bit here, but we'll see it more in organic chemistry. Why? The structural formula is almost like a map. It's not really a map, but it shows you where the atoms are located and what they're bonded with. So it focuses more on the overall arrangement, like a seating plan, right? But you have a molecular plan. So there is a purpose to this, and it helps you to sort out where the elements are relative to each other. Empirical formula, this shows you the relative amounts of each element in the compound. So let me actually, instead of defining them all here, let me actually go to their definition and I will explain it there. We're told an empirical formula gives the relative number of atoms of each element in the compound. I just said that. It is the simplest whole number ratio representation of the type and number of elements present in the molecule. So let me make this a little bit more relatable. If we were in a classroom, right, and I'm trying to figure out how many females are there to males in the classroom, okay? So let's say this class had 5 females, and then let me pick a number. Let's say 10 males. This is just a number I'm picking. Then you would say, oh, well, this is my class. It has 5 females and 10 males. If you were to give the empirical tends to also mean fundamental, the basic, the bottom line. If you were to give the empirical relationship between the number of females to males, you would say, oh, there is one female, if I can spell female, oh my goodness, per for every 2 males, okay, per 2 males, or for every 2 males, for every 2 males in my class. So for every one female that showed up, 2 males showed up. You're talking about a simple whole number relationship. You're relating one to the other. And that's the purpose of the empirical formula. We're trying to realize how one element relates to the other. So for every one female, we have 2 males that showed up. Now, when it comes to molecular formula, we're not giving a simple whole number relationship. We're giving the actual, like giving the role. How many showed up? You say 5 females, 10 males, end of story. Okay, so molecular formula, you're actually giving the amount of the elements or the atoms in the compound, not the relative simplified amount. So the key term here is the simplest. You have to divide and get the whole number relationship. Let me see. Okay, so I will go through this slide right here, and then yeah, and then we'll be done. So for this part here, we have C4H8. C4H8, you can see right here. This is showing you the actual number of elements we have in the compound. There is 4 carbons in this compound, and then there's 8 hydrogens in this compound. Now this will be called the molecular formula because it shows you the actual number. It's like you're doing roll, right, of the elements that showed up. Now when they're saying find the empirical formula, how the numbers relate to each other, the simplest divide whole number relationship. That's how you get this. You want to divide. So you want to find the greatest common denominator. C4H8. The greatest common denominator here is what? It's 4. Is it 4? Yeah, it's 4. Divide both numbers by 4 and you get 1 and 2 here. So that's how you end up with this. So the one that gives you the bare bone relationship, for every 1 carbon, there are 2 hydrogens. This is the empirical formula versus molecular formula. So for this one again, you have a molecular formula here, 2 borons for 6 hydrogen. When they ask you to get the empirical formula from this, divide by the greatest common factor. B2H6, let's see, 2, right? Divide by 2, divide by 2. This becomes 1, this becomes 3. We get this formula right here. Empirical formula for the molecular formula is for every 1 boron, we have 3 hydrogens. Okay? CCl4. CCl4, this is the formula. So this is the molecular formula, right? CCl4, greatest common factor, 1. You get the same thing. So this is both the empirical formula and the molecular formula. So what can we conclude? For a formula like this, the empirical formula can equal the molecular formula because it can't be simplified further. Okay. Remember I told you the structural formula does show you how the elements are shown. So yeah, this is the structural formula right here. So technically, the structure formula would be more like this. I just thought about it this like this. Like who I don't know how you pronounce that. HOOH. Just telling you that when you write this formula out, make sure the oxygens are in the middle and then the hydrogens are on either side. So this is actually a better structure formula. This is a structure. But it shows you right here. When you draw this out, the oxygens have to be in the middle and then the hydrogens on either side. So it's more like that versus like this. And we'll talk about that later on, why it's like this and not like that. I think we already did this, right? Huh? Look at that. So we are done. So what I'm going to do is when we start on Wednesday, we'll start here. Yeah, we'll start here. Okay. Okay, guys. This is what I have for today. If you guys have any questions, please let me know. My goal is to get this done before the spring break. I don't want to carry this on into the spring break. So I'm looking at how many slides I have left, and some of the stuff I'll try to go through a little faster because there's a lot, little structures and everything. But yeah, okay. I will talk to you guys on Wednesday. Have a nice day.